Got some demos here of magnetic induction, and so this first one is to demonstrate the repulsive. Well, let's see. Actually, let me do this one first. This is the one I want to do first. I'm going to get a current flowing in this. There's a coil here, a solenoid coil with a piece of iron stuck in, really intensify the field, and so I'm going to get current flowing in that. And then here I have a copper, another coil, lots of turns on it, attached to a resistor which lights up, in other words, a light bulb. Have I overdone it on that one? Let's see. Yeah, it heats up and then it cuts itself off. I think that's what's happened. I already got it too hot when I was playing with it before the class. There we go. It's too hot. I have to let it cool down. That's also going to be my ring launcher. Okay, so over here, here's just a piece of aluminum, looks like, in a circle. And another piece of aluminum, but there's a slit. In this one, you can see here, there's a slit cut in it. So the current can't flow as freely through that, through the circle. And this is a very sharp needle that I found out. I don't know why it needs to be so sharp. Okay, I need to try to straighten that out a little bit. Okay, so now if this is a pretty hefty magnet, these things bite. If you get your fingers pinched by them once or twice, you learn to try to be careful with them. And now if I push the magnet towards the coil, if it could spin more freely. I bent the needle before class. There we go. It can push the loop around like that. Remember, we found that the induced current is in the opposite direction. Opposite currents repel. And this one, doesn't work as effectively, and that's because the current can't flow freely around the loop. Okay. Can't flow freely around the loop, and so it's not as effective at pushing it around. Okay, so that shows the repulsive interaction. Let's see if this is cooled off enough that I can get this to go. No. Oh, I overheated it. Yeah, Terry warned me about that, and I went and did it. Okay, hopefully after another minute or so it'll cool off. Okay, so here is a copper pipe. I'll try to bring this camera in on this. And the copper pipe has a light, just a flashlight here at the bottom, shining up so that you can see it clearly on the camera. And now I have just a marble. It's steel marble. It's not magnetic particularly. And if I drop this into the pipe, it doesn't take long for it to get down to the bottom, right? You heard it fall. If I take instead a piece of magnet, series of magnets that have been stacked up together, and I drop it into the pipe, you could see it there for a second. Even when I dropped it in, it took a minute for it to drop down into the top. And you can see it's taking its taking its time to get down to the bottom. And of course, we figured this out in class last time, why that should be taking time. Okay, now I have a question for you in addition to this while we wait for this to happen. Gravity is doing work, but there it is. It ends up with not much speed when it gets to the bottom. So there's not much kinetic energy in this thing at the bottom. So what's happening? Where does the work done by gravity end up? It's not in kinetic energy. For the magnet, what is it?
Force pushing down on the pipe.
Okay, it's got to be work. It's got to be energy.
Yeah.
We're talking about, right? Not force. It's got to be an energy we're talking about.
There would be current in the pipe, correct?
Yes, sir. There's current induced in the pipe, but it goes away as soon as the magnet's dropped. Mr. Bicot.
Is it used to hold the magnet up?
That's a force. Yeah, so there, when you say hold it up, right? Am I doing any work?
Well, like
no.
It's giving it energy to go down, which is then giving the pipe a current.
It's giving a current, right?
Which is then holding it up, which is then reducing energy.
Yeah, I'm looking for a form of energy here. So we've seen it before at work, potential energy, kinetic energy. There's another form of energy that we've encountered in binary collisions when they're not elastic.
So dissipated.
Yeah, there's a dissipation going on somewhere, right? Something is dissipating. What is a form of heat? Yeah, the pipe is heating up. It's not. I can't even tell, but it would be measurable. Why is it heating up? How does it heat up? How does it heat it up? Whenever you have a resistor, a resistor is a dissipator, right? It heats up the resistor. In the case of the light bulb, it heats it up enough to create light, visible light. So when there's current in any sort of conductor, there's a non-zero resistance, right? It's not a perfect conductor, so there's some resistance. And that resistance, anytime current flows in a conductor or in a resistor, a non-perfect conductor will heat up. So there's a little bit of heating because of the current flowing in the pipe, and that gets dissipated. That's the what would have shown up as kinetic energy is now showing. That's a bad one. There, that shows up as heat in the pipe. Mr. McKenna.
If you had a superconductor as the pipe, how would that act differently?
Yeah, that's a good question. And I got to think about it for a minute. Depends. So there's two different kinds of superconductors that we have to deal with, and I think the answer is it would stop moving. It would go down and stop in the pipe, levitate at that point. There would be a permanent balance between gravity and the force because of the induced current. So you can levitate magnets on top of superconductors. They'll stay there. Mr. Bicot.
If the magnet's not moving, then how is it still inducing the current?
So the current doesn't need to be replenished. Once it induces a current, it stays there forever because the resistance is almost zero. I mean, it's really small resistance, so the current is virtually permanent current. So it doesn't need to be replenished. So it just balances, and it will balance the force. So the first motion induces the current, and then the current is enough to keep it suspended. It's a little more complicated than that for a superconductor because the magnetic field here will penetrate the metal. In the case of a superconductor, type 1 superconductor, it doesn't penetrate. The magnetic field doesn't penetrate. It's a little more complicated. I've oversimplified it a little bit there. Okay, so let's see if I can get this thing to work. There we go. Okay. Got it to light up. And I was warned by Jerry, don't do this too hard. It's breakable. That was pretty good. It wasn't too bad. I got the current flowing, pumped current into the coil, and that induced current in here, which was caused a repulsive interaction. Okay. Obviously, you can get pretty good about that. Okay, let's see here. I need to back up on. I need to switch over to the lecture capture here. It's not showing me what I want to see. There we go. Okay. I may not have actually gotten this on the tape. I'm thinking on the recording. I think I didn't. Zoom out a little bit. Okay. All right. Now let's see here. I'll take a couple of or just one volunteer would be good, as long as you're careful. Mr. McKenna? Okay, you see we keep these separate from each other. We don't let them get too close together. There's a piece, one's outside the, so I think the magnet's on the inside, so you can pull the other one off there.
Strong one.
All right, so that's just the steel, I think, just the steel marble. Careful with these things. Okay, try rolling it down there. No, that's not. Try that one. There we go. Okay. We've done that problem before, right? Last term we talked about rolling things, rolling spheres down inclined planes. That one has reached a terminal velocity, right? It's a steady, uniform linear translation. So obviously there's some balance. The induced forces must balance.
Okay.
Yeah, but it's kind of, yeah. Okay. Let's start it over again.
Okay.
That's a nice extra credit problem. See if you can figure out, it's obviously magnetic induction, but it's not a closed circle like we were doing here. But it's still working somehow. Something's going on there. It's obviously a different geometry because the thing is rolling that way. The magnet's changing its orientation as it rolls. It doesn't seem, I don't have to seem to, Mr. McKenna didn't have to be careful to line up the magnet, North Pole, South Pole. It just kind of rolled down. Doesn't matter how it's lined up. Okay, that's an interesting problem to figure out how that one works. Mr. Picot. Thank you, Mr. McKenna.
It doesn't matter that it's not a circle.
Right. Obviously it doesn't. Yeah. Yeah, it did over here, right? We noticed that there was less effect. And if I take this copper pipe and I make a slit down the length of it, then the magnet will drop much faster. It won't drop as fast as the unmagnetized bullet or marble, but it will drop faster than if it's complete. So there's still some induction and still some resistance going on, even if it's not a complete circuit. And this one is pretty effective. So, okay, this is more complicated to figure out. Still the same principle. It's just somehow how does the induction cause a force that opposes gravity in this case. Okay, so let's see here. I want to go to this now. Maybe I'll take this down.
Would it split the bow down if it was just a flat plane?
Good question. Yeah. If you had a flat plate and the magnetic marble like that, we're rolling down the flat plate, it would still be the same thing. Or does it have to be a V shape? Good question. Okay, so let's see here. We were talking about then the inductive effect can take the form of a force on charges, and we said that there were actually two different places where this could occur. One is the V cross B term, the V cross curl of A, that we've talked about before, and that we saw in magnetostatics. And that force is perpendicular to the velocity and perpendicular to the magnetic field. It doesn't increase the kinetic energy, doesn't change the kinetic energy. It can produce a circular motion. For example, a charged particle in a uniform magnetic field would just move in a circle. Now, the other term here is not proportional to the velocity. It's proportional to the rate of change of A, the A dot force. And that's different in the way it acts because it doesn't depend on the velocity of the test charge. So it has a different mechanism for causing a force. And in fact, it produces a force that resembles an electric field in the sense that it works on a particle that's at rest, whereas the other one doesn't. So you can see here something of the nature of the A field shows up here. Remember, we were talking about how does the A field relate to the B field. Well, the V cross B term, the last term there, is obviously a relation to the B field, but we can't express the A dot in terms of the B field. It must be explicitly written in terms of the A field. It gives a further specification. It includes, if you read carefully the inside front cover on the A field, it talks about it actually gives more information than the B field because this A dot effect is a magnetic effect, but it's not easily expressed in terms of B. So remember, A is a magnetic field. But it's distinguished from what we typically call the B field. So the A field and the B field are interrelated, but the A field actually gives some information that the B field doesn't, and in fact it leads to this force. Okay, so now let's look at Faraday's law and Faraday's disk. Faraday's law is written this way. So if I go over here to this, let's consider the secondary, and I just draw a circular loop. And I want to look at the forces produced on charges because of a changing A field. So the force on a charge that's present inside of this wire is of this form here. It's of the form of the related to the A dot. Let's first, before we do that, before we do the circle, let's go back and remind ourselves that we had a current carrying wire. Current is in this direction, produces an A field, right? We illustrated this in the lecture last time. If we put a bead on a wire, a charged bead on a wire so it could slide up and down, and if we look at the force, this force, if the A field is changing because the current is being either decreased or increased, and if we integrate the force over time, the integral over the force over time, no dot there, integrate the force over time, that's the change in momentum. That's caused from one time to another. That's the change in momentum that's caused by the change in the A field. And so this is then the time integral of the derivative of A with respect to time. So this is minus Q over C times the change in the A field at that point. So the change in the momentum of the test charge is proportional to the change in A, but with the negative sign. Remember that negative sign is important, and that's what leads to Lentz's law. It's an opposing effect. It tends to oppose and restore what was present before. Okay, now let's go back to a loop. Now, suppose we have a bunch of charges in the loop that are being subjected to a changing A field, and the A field, of course, has a different value everywhere, possibly different value. Let's follow the motion of a single charge around the loop, right? The current has been induced, and so let's follow that charge all the way around the loop. Now we're doing an integral of the force around a closed path. So this would be the work done when that charged particle moves all the way around the loop. Okay, and that force is proportional to the time derivative of A dot dl. This is called the EMF. It's the electromotive force. If I divide by the Q, it's the EMF. It depends on the force produced by the changing A field in that loop. Okay, now if the loop is stationary, then I have a combination of two things. I have an integral, but I also have a time derivative. But if the loop is stationary, I can interchange the order of those operations. In other words, if the loop is stationary, it should be a partial derivative of A with respect to t. Let me clean that up a little bit. I can interchange the order of the differentiation and the integration. If the loop itself, if the path is not changing in time, then I can change the order of those operations. Okay, now this piece we can treat using Stokes Theorem. This is the integral of A around a closed path. It's the circulation of A around a closed path. And this is we're following it inside of a wire, so this is a real path in that sense. But remember, Stokes Theorem applies to any path. It could be an imaginary path. Okay, now by Stokes Theorem I can relate this to the curl of A, integrated over a surface here. I'm going to use ds to integrate to call the surface. And so I'm changing this path integral around the closed path to an integral over the surface area that's bounded by that path. So this C is the boundary to S. That's Stokes' theorem, and that's true for any field, not just A fields, but any vector field. It's, remember, it's kind of a variation on the fundamental theorem of calculus. Okay, but what is the curl of A?
B.
It's the B field. So this is the flux of B through that path. It's called phi, capital Phi B. It's the magnetic flux. We've encountered electric flux. Remember, we looked in Gauss's law. We looked at the electric flux through a completely closed surface was 4 pi times the charge enclosed by the volume. This is over the surface that borders a volume. It's a closed boundary to a volume. That was the electric flux. So we've seen something like flux before. We've also looked at current flux. We integrate the current over an area, the volume current over an area. That gives us the total current that passes through that area. That's a current flux, charge flux. So we have magnetic flux here, and it's just counting, looking here, how strong is the magnetic field when passing here. And this is the magnetic field generated by that A field, right? That's related to the A field that's changing. So we have some magnetic field that's passing through this, and we want to add that all up, and that gives us our total magnetic flux. And so the magnetic flux, the path integral of A around the circulation of A is related to the magnetic flux. Well, if we go back to our calculation of the EMF, we said that the work done around the closed path because of the changing A field is then minus Q over C times the time derivative of this magnetic flux. And then there was the time derivative. We interchanged order, so there's still a time derivative. So the time rate of change of the magnetic flux will induce a current in the secondary. So this is another way of expressing it. Fundamentally, this is what you want to start with. This is more fundamental. It relates the force on any charged body to the time rate of change of the A field. And this is in CGS units, of course. But you can rewrite it in this fashion. This is called Faraday's law. But Faraday's law is very compact because you just look at the magnetic flux and the time rate of change of the magnetic flux. And so you can, going back to this experiment that I did here with the loop here, the secondary, and you can see this as magnetic flux pushing now, increasing amount of magnetic flux through that loop. And so pushing it closer increases the amount of magnetic field that's going through there. So we get an increasing magnetic flux that pushes the loop away. Okay, so taking out the charge, this is the induced EMF. The induced EMF is the work done per unit charge. The EMF is the work done per unit charge. It looks like a voltage, like a battery pushes electric charges around in the wire. Well, this induction, a changing A field, also does that. And it will work on stationary charges and give them impetus, push them through the loop. Okay, but Faraday's law is not the most fundamental, and in fact it's possible to get confused with Faraday's law. And that's why I want you to keep this in mind. I should say this is 1 over Q is the EMF, or let me write it. EMF times the charge. Okay. So the most fundamental thing is the Lorentz force. This term, remember the 3 terms in Lorentz force. Go back to the Lorentz force. Follow the charges and look at the forces that are present on the charges, and then you won't get confused. It's possible to get confused using Faraday's law, and here's an example of a confusion that can happen, which is Faraday's disk. So Faraday's disk has a metal disk that's being spun like a wheel around its axle. There is a magnet, a U-shaped magnet that's placed on it, straddling the wheel. And then there are contacts placed on this. Let's see if I'll pull this down. I can point to the contacts here. Change this. So there's electrical contact on the outer surface of the wheel, and also another electrical contact on the inner part of the wheel, and that circuit goes around. Okay, now this induces current in that circuit that's placed around between the two contacts, the contact on the inner part of the axle and the part on the outer part of the wheel, then make a complete circuit. That will push current through there. But the puzzle here is, if you look at it in terms of Faraday's law, you're looking for a change of magnetic flux. It's hard to find anything that would be changing magnetic flux on this. Certainly the magnetic flux through the wheel doesn't change. So that gets to be kind of a puzzle. And the way to solve that puzzle, let's see, here's the illustration of the setup a little more schematically. In orange you see the circuit there, and you actually get current flowing in the disc, in the wheel itself, from the center to the outer rim. And you see the magnetic field can be uniform. In this case, we sketch it as being uniform. In the actual setup you saw, the magnetic field's not uniform everywhere. We had this fringing fields all over the place. But we could set it up, and we still get the same effect if we have a uniform magnetic field. But it's not clear how to identify a changing flux in this thing, a magnetic flux that changes. Instead, if you follow the charges, remember we go through this, look at the charges and the forces that are present. And so these charges are moving in a magnetic field. If you look at the charges that are flowing from the wire through the wheel, let's go back to the here. They're having to move from the center to the outer part of the wheel, right, in order to flow through the circuit. And there's a magnetic field that's present. So what force is present on them? Well, if they're rotating also, right, then there's a V cross B effect, V cross B term that pushes them outward. And so that's the origin of it. But if you just stick with the Faraday's law, the phi dot, it's really an incomplete thing. So it's much better, if you're trying to understand what's going on, to go back to the fundamental forces that we talked about. Okay. So here's the bottom line, and these are the basic principles that I want you to remember related to magnetic fields. And the electric field, what we know so far, as of this far. A charged body, which I abbreviate to discharge, but it's a charged substance, but a charged body conditions the parts of the plana around it to have an electric field, which is further specified by phi. An impetus-activated charge conditions the parts of the plana around it to have a magnetic field, which is also further specified by the A field. And this conditioning is passed along to more parts of the plana, from one part to another part. Okay. Once the parts of the plana have these fields present in them, they can act on other charges, other charged bodies. There's the phi force, the V cross B force, and the A dot force. Those are the three terms. So that's the way I would like you to understand the electromagnetism so far. You know how to calculate. You know how to understand the E field and the phi field and the A field and the B field from that. And if you stick to the force, the Lorentz force expressed in terms of phi and A, everything will be, the causality in the causal structure is quite clear. And that's really the thing to take home. Okay. Yes, sir. Mr. Picot?
Is there any reason you didn't put the C in for the V cross?
I just forgot it. It should be there. Thank you. Yeah, the second line at the bottom there should have a 1 over C term in it. Thank you. Yeah. Okay. Okay, so now let's imagine some circuits we could make out of this. If we had a primary, and I'm going to draw a circuit with this, and this is represents an inductor in circuit diagrams. It looks like a spring, but it's a coil. And the idea is to generate stronger magnetic fields by wrapping the wire around many times. You could put a iron core will enhance the strength of the magnetic field as well. Ms. Wheeler, did you have a question?
I have a question about going back to the derivation of Faraday's law.
Yes, yes, ma'am.
So it was originally it was like when we started it was the partial derivative of A.
Yes.
So is the derivative of or the derivative of the flux with respect to time, is that like a partial derivative?
Well, it's the magnetic flux is reduced to now a function of nothing but time.
Okay.
And so there's really no distinction between a partial derivative and a total derivative with respect to time in that case, yeah. She's picking up here, very, very carefully picking up that I switched here from a partial time derivative right here. And then I changed that line integral into a surface integral, which became the magnetic flux. And then I took the time derivative of the magnetic flux. And I didn't seem to distinguish any more between a partial derivative and a total time derivative. So A here, remember the A field depends on location and time, and that's why we write a partial derivative, because it's the time dependence of the A field at that place that produces a force on a charge at that place. So it's a partial derivative with respect to time, keeping x, y, and z fixed. Whereas now we've done this integral here over the surface, we've integrated out all where the B field is. As long as this path isn't moving, then I can do this quite clearly. And as long as I'm not moving the secondary, for example, then I can rewrite this then as a phi dot, because phi doesn't depend on anything except time anymore. So the distinction is gone. Yeah. Good question. Okay, so I'm going to make a circuit with an inductor in it. And so let's take, for example, have a switch like this. And here, let's put a battery in it. I need a battery. We'll put a battery. So this is all coming back to what we were doing at the end of the second chapter very briefly. We have a resistor, we have a battery that produces a voltage, we have a switch. And now we put in an inductor. Okay, so clearly we could have a second circuit over here, which might have, for example, a resistor, but no battery connected to it. And I'm going to take off that L for a moment here. The primary, when we throw the switch in the primary now, we get current flowing in the primary. That's a changing A field. Will induce current in the secondary. And the coupling between those two depends on the geometry. It depends on how close it is and how the windings go. So how strong that coupling is between the primary and the secondary coils depends a lot on the specifics. So the strength of that coupling is called M, the mutual inductance. The voltage across this secondary inductor here, the secondary coil, is proportional to the change in the current in the primary. V across the secondary there is proportional to the rate of change. And I'm just going to put a symbol M here. So the voltage across that secondary coil depends on the rate of change of current in the primary, and all the other factors of geometry, distance, number of turns in the coil, all that sort of stuff is lumped into M, the mutual inductance. But by closing the switch in the primary, I can induce a current in the secondary, and in fact, if that resistor is a light bulb, it'll light up, right? That's we almost did that, except I was moving the secondary in that case, right? When we were doing this experiment over here. Okay, yes, sir, Mr. Luker.
So would you get the same effect if you were just moving the primary?
Yes, that's right. Yeah, if the current is steady in the primary. But in that case, there's not an I dot, right?
Right.
Yeah. In that case, so that the expression is more complicated. So let's suppose that these circuits are stationary. Mm-hmm. We're putting them on a circuit board, and
there's like the same effect.
Yeah, that's right. Well, so
The same cause.
it's actually the same cause in that case. That's right. Yeah, it's the A dot in both cases. Moving the primary or changing current in the primary induces a current in the secondary. It's an A dot. So the A dot, the A dot effect, the A dot strength of the A dot in the secondary depends on I dot in the primary, right? How fast A changes depends on how fast the current changes. If I'm leaving the primary fixed and the secondary fixed. And so this is like having a battery in the secondary circuit there, in the sense that there's a EMF across the secondary that now starts pushing charges through the secondary. So I have now two circuit equations. I would write Kirchhoff's law for both circuits. I would have a circuit equation for the left circuit, which involves the voltage across the battery, the voltage across, and I have to talk about this primary coil here in a second, the resistor, and then I have a circuit equation for the secondary, where I have the voltage across the resistor and the voltage across the inductor, the coil in there. Okay. All right, but that's not the end of the story. It actually gets a little bit more complicated because, as you picked up on there, the feedback mechanism is going on here. So there are numerous ways that we can get feedback going on. One of them is that there's a self-inductance, that this part of the coil up here sees a changing A field because of another part of itself, another part of the coil. And so there is a self-inductance that goes on. So even if I don't have the secondary, I've got something kind of interesting. So let's just go to a primary by itself. And this we haven't really considered yet, but you can see how this is going to come about. Here I have a battery with a switch and a resistor. And previously we put a capacitor. Let's just put one of these coils here. So now when I throw the switch, God bless, it wants to try to start pushing current through. But when it starts pushing current through, there's a change of current now in the inductor, in the coil. And that produces a back potential that tends to slow down the increase in current. So this is an RL circuit. Now remember, the inductor is also dissipative. It's dissipating heat. I'm sorry, the resistor, excuse me. I said that exactly backwards. The resistor is dissipating heat. The inductor is not. And we also have the battery here. So now we have a circuit equation that connects the charge on the resistor and the current flowing through the inductor. The voltage drop across these two. So the voltage drop across the capacitor, remember, is Q over C for the charge that's on the capacitor. And for the I'm sorry, excuse me, I stuck a capacitor in there. Why did I do that? There we go. Current flowing here. Sorry about that. We have current flowing through the resistor, current flowing through the inductor. The potential drop across the resistor is IR. The potential drop across the inductor is the self-inductance times the rate of change, the I dot of the current. Okay, and it starts off. We would start off when the circuit is thrown. The switch is closed. The current initially is 0, but it's changing. There's got to be an I dot. And so all of the potential now, there's no potential drop across the resistor. All the potential drop is across the inductor. But now the current will build up because there's an I dot. It will build up. And eventually it will increase to the point now where it becomes a constant. The current is a constant, and all the potential drop is across the resistor, and there's no change in current, so the potential drop across the inductor has gone to 0. So let me sketch that out. At t equals to 0, when the switch is thrown, the initial current is 0, but the current change of the current must be the voltage on the battery divided by the inductance. Has to be increasing in current. So now the current's got to be changing. It's going to be building up current in that. But then at a very much longer time, means much later, so I'm going to indicate that by we wait a really long time. The current has become a steady current now. So the change in the current goes to 0. And now the current that's flowing through is equal to the voltage divided by the resistance. So based on that argument, we would say that the current flowing through the circuit, when we turn on the switch, will look like this. It reaches a maximum value of the battery voltage divided by the resistance. And that slope here, the initial slope, is the voltage divided by the inductance. So this differential equation has a simple solution to it. I of t will equal to v over r times 1 minus e to the minus t over, is it LR? Yeah, must be LR. Is that right? LR. Hang on. All right. We're going to do it's going to be exponential in time. We got to find out what alpha's got to be to solve the differential equation. Okay? But check here that I of 0 is equal to 0, right? Because the exponential is 1. 1 minus 1 is 0. Let's check the initial. Let's take the time derivative of this. So this is v over r alpha e to the minus alpha t. Okay, and then at time 0, this must be, this is v alpha over r. This must be v over L. There we go. So alpha is equal to r over L. There we go. That's why it didn't look right. So that's what happens when you take an inductor and put current through it. There's some resistance in the circuit. And so it'll build up current gradually. And the time that it takes to build up is determined by that combination of R and L. So we see here by dimensional analysis, what appears in the argument of this exponential must be dimensionless. And that means that L over R, inductance divided by resistance, must have dimensions of time. So that gives you the time constant for this ramp up in current. That time constant is determined by the combination L over R. Okay. Okay, now, yes, sir.
Would
Mr.
we
Galvin.
ever speak about a changing current as an acceleration of charges?
Okay, now, yeah, okay, it's very tempting, and I was about to point that out. Let's hold on to that question because you'll see he's getting at here something that looks like an analog to a mechanical system. So let's go draw a circuit. Before we had resistors and capacitors and things. So let's go draw. I got to move this down. I need to insert it here. Let's go expand the circuit to include a capacitor now. A resistor, an inductor, a capacitor, and a switch. So there's a battery, a resistor, an inductor with self-inductance here. It's just a single circuit. We're not talking about secondaries at this point with a capacitor. Again, we could apply Kirchhoff's law. And remember, when we're doing Kirchhoff's law, there's a charge on the capacitor, but there's also the current in the resistor and the changing current in the inductor. But remember that the current is related to the charge on the capacitor, because as the current is flowing in the circuit, the capacitor is charging. And the current that's flowing through the inductor is the same current that flows through the resistor. So the I dot that's flowing through that's attributed to the inductor is the same It's the time derivative of the same current that's in the resistor. So here's what I'm going to write down Kirchhoff's law for this circuit, Q over C, but I'm going to write it all in terms of Q. This is summing up the voltages around the circuit. All in terms of Q, the charge on the capacitor, from which we can determine by derivatives the current that's flowing in the circuit. Okay, if we had current flowing in the system and we chop out the battery, we switch out the battery, for example, the circuit equation would be this. This is the circuit equation without the battery. It's the same. Anybody picking up on something here? Mr. Dowdle, I think, was starting to pick up on it.
Analogy to acceleration and position.
Yeah, that's right. This is looking like the differential equations we were using for a simple harmonic oscillator with damping. So I'm going to write down the simple harmonic oscillator with damping. Let's write it all in terms of x. Plus plus. If we put it all on the same side, there we go. So I can rewrite Newton's equation for a damped harmonic oscillator. It looks like this. So there's an analogy going on here. Be careful about extending analogies, right? Analogies you have to be careful about. Analogies have their limitations, but there's a formal mathematical, certainly, analogy between a damped harmonic oscillator and this circuit. And the analogy here, let's sketch out the analogies, the things that are analogous. The inductance is like a mass. Well, I think we should go back first to X and charge. Let's do that. X, the charge is analogous to the displacement in the simple harmonic oscillator. The mass is analogous to the inductance. So it's a kind of resistance to an impetus, the inductance is. And the impetus would be something that's an analogous impetus. When the current is flowing, there's something like an impetus. Impetus of charges, yes, we've talked about that. Okay, but you've got to be a little careful about stretching this too far. The resistance is like a drag. And the inverse capacitance is like a spring constant. And it used to be fashionable, in fact, to study mechanical systems when people were building bridges before they had computers to analyze the dynamics of bridges. They would actually make circuits, analog circuits, with scaled versions of these constants in order to study the dynamics of a system. Could you find instabilities in the system? You've probably seen pictures of bridges and things that get into oscillations because they were driven at a certain frequency. They used to study those things by making electrical analogs and scale all the parameters in the circuit to match the coupling, the constants involved. Of course, you could get much more complicated than one simple harmonic oscillator, right? You could have coupled oscillators connected together, and in which case you'd have several circuits connected together. Okay, Mr. Dowdle.
And so wait, would the solutions to the differential equations be pretty similar?
Very similar. Exactly right. Mathematically, they're they're analogous. So the mathematical formalism is the same. The solution to the differential equations looks very much the same. So let's take an example here, just to hold you just a second. I've still got another minute. Let's drop out the resistor. So we have a capacitor and an inductor, like this. And there are various ways. Suppose we could get current flowing in this thing. The circuit equation looks like, what does that look like? Formally. What's that?
No way, resistance.
Harmonic motion without damping.
Motion without damping. It's the simple harmonic oscillator. right, without damping. The equation for that was just this. And we wrote down the equation. The general equation for that from before was an amplitude times the cosine of a frequency time plus a phase shift. That was one way of writing it. So we could write Q of t for this is going to be some amplitude times cosine omega t plus delta. What is omega? What was omega from the simple harmonic oscillator in terms of k and m?
Square root of k over m.
Square root of k over m. So what is the frequency of this LC circuit? No, is that, let's see, k, I've got, it's exactly backwards, it's 1 over this, isn't it? 1 over root LC. Yeah, 1 over root LC. Okay, so what would the charge on the capacitor look like as a function of time? It oscillates with the frequency determined by the inductance, the self-inductance of the coil, and the capacitance in the circuit. That's a clock. It's a way of setting up a simple clock on an integrated circuit. In fact, that's what they do. The driver clock on PCs and your cell phones and things like that are these LC circuits. Maybe a little bit more sophisticated, a little bit more complicated than this, but it's basically that. The driver clock, you can clock something, right? The speed on your processor speed is determined by the clock, and you can overclock something. It makes it work hotter, but you can get faster results if you do that. So that's an example of an analog between a mechanical system and these electrical systems. Okay. All right. Any questions? Okay. We'll see you on Wednesday.